now. Stop it. Okay. Now, so last time we started dealing with the full rank least squares problem, and I mentioned two ways to solve it. You either solve a normal equation and solve them. But that's a very efficient system. So the other way is to use a QR factorization and solve a system which would have conditioning similar to that of A itself. So what I did not discuss at that time was how to compute the QR factorization. So to show different approaches over the next few class periods. I want to check the schedule here. Okay, yeah. So 3 class periods on how to compute QR. So Givens rotations today. Household reflections on Thursday, and then next Monday, Gram-Schmidt, which is something you would have been seen in an earlier linear algebra class. And but it's actually the worst method of the 3. Okay, so well, Givens rotations were not actually invented by Givens. They were invented by Jacobi. There's a number of algorithm which I won't actually cover for computing eigenvalues that uses the exact same rotations. And because that algorithm is called Jacobi method, they're called Jacobi rotations over there. But I guess I'd have to check the history. I imagine they're called Givens rotations here because maybe Givens was one who used them. For this purpose, we're dealing with the QR factorization. All right, so goal is to take M by N matrix A and factor it into a product of M by M matrix Q. Our assumption for now is still N greater than or equal to N times a matrix R with the same size of A. Q is orthogonal. Transpose Q equals Q transpose to identity. And R is upper triangular. So with the least squares problem, we would end up solving a system involving R using back substitution. So there are certain similarities between what I'm going to show you here and Gaussian elimination. Gaussian elimination, you take A, you multiply it to the left by a bunch of elementary row matrices that are unit lower triangular to reduce A to an upper triangular form. So the process will look something like this, where you start with A, and then you multiply on the left by certain matrices, with the idea of reducing A to upper triangular form. So, but the thing is, these matrices Q1, Q2, up to QK, which if multiplied together in the opposite order and not transposed, would give you Q. So these are not elementary row matrices, but rather each matrix Qi is orthogonal. And you can show that if you multiply two orthogonal matrices, the product is also orthogonal. Just as, so orthogonality is preserved under multiplication and inversion, just as triangularity is preserved under multiplication and inversion. Okay. So before I show you what kind of matrices these would be, to eliminate entries below diagonal, if we already have a way of multiplying A by rather simple matrices to eliminate elements below the diagonal, why not just use those? Why not just do Gaussian elimination all over again? The reason why is because if we want to reduce A equals B to an upper triangular system, the reason is because the norm that we're trying to minimize, B minus AX, would not be the same as, like, if I multiply this by L inverse, which is what happens when you're performing all the row operations of Gaussian elimination, we'd be solving this upper triangular system, where L inverse B is a vector Y from the Gaussian elimination algorithm. We've changed the problem. You remember last time, whereas by contrast, the norm of B minus, two norm of B minus AX is the same as Q transpose B minus RX. So it's because multiplying by an orthogonal matrix preserves two norms. That's why we take this approach instead of Gaussian elimination. Because, yeah, we can go ahead and solve that, but then that X won't minimize that. Okay. So, all right, so what's the counterpart of row operation? Instead of finding a multiplier, what do we do instead? So we're going to derive a given rotation. Find numbers C and S such that, let's go show you like a 2x2 case. Mine's right here. Okay. So we're going to perform a QR factorization of a 2x2 matrix. All right, and so we want this 2-1 entry to be 0. So this is our Q transpose A is equal to R in the 2x2 case. So what we could do is carry out the multiplication. So we have, okay. So we need Q transpose Q to be equal to identity. So Q transpose is C minus S SC transpose. Then we have C minus S SC equal to identity. So then, if I carry out this multiplication, then I'm going to have C times C, and then this is transpose, so I'm going to have plus S times S. C squared plus S squared is equal to 1. And then for the rest of it, I'm going to have C minus CS plus CS equals 0. So that was satisfied automatically. And then I have CS plus CS. All right, so that's satisfied automatically. And then for the last element, I have S squared plus C squared equals 1 again. So I'm setting up a matrix to have this form. I get C squared plus S squared equals 1. But what does this remind you of? Cosine squared plus sine squared equals 1. So we can say that C is equal to cosine theta, S is equal to sine theta, for some theta. We don't know what theta is yet, but it's something we can keep in mind. All right. Okay. So we'll take that into account when trying to find C and S. Okay. Now, to make sure that the 2-1 entry of a product turns out to be 0. So R21 equals 0. That means when I carry out the multiplication, I'm going to have minus SA11 plus C times A21 is equal to 0. All right. So if I move the sine term to the other side and square both sides, I get that. But now C squared is, so sorry, S squared is 1 minus C squared from what we saw earlier. Okay. So now I can use this equation to solve for C squared. So C squared turns out to be A11 squared over A11 squared plus A21 squared. Now, if I take a square root of both sides to find C, I have a choice of a positive or negative square root. So I get to just choose a plus sign. So that is my cosine part. Then to find the sine part, the best way to do that, and unfortunately that one I did in the book, but it is a better way to do it. I can take this formula for C and substitute it in here. So I have, if I take this equation and solve it for S, then what I get is going to be C times A21 over A11, assuming that A11 is non-zero, at least. In that situation, we can do it later. So if I multiply this by my C here, then wait, something is wrong.
No, it's okay.
Hold on. Okay. Yes, okay, this is what I want, okay. So that's so same denominator, it's different, the numerator swap. Okay, so that is how I get my cosine sine pair. All right, any questions about how that was arrived at? Okay. So, in general, matrix G given by C minus S S C. Where C is equal to A over square root of A squared plus B squared. S is equal to B over square root of A squared plus B squared. Is the Gibbons rotation that has this effect. D transpose times the vector AB is the vector R0, where R is the magnitude. So this vector, so R is the two norm of a vector we're applying the rotation to, and since G is orthogonal, it's going to preserve that norm. So it basically takes all of the magnitude of this vector and puts it in this one element here, and the other elements have to be 0. So if A11, or A in this case, if A in this case turned out to be 0, which would have messed up what I had over here, it would have caused some difficulty. Then so the cosine would be 0, so either the angle would be pi over 2, but S would turn out to be it would end up turning out to be the sine of SIGN, not SINE, the sine of B, because if A is equal to 0, the denominator would be the absolute value of B. So S would be equal to plus or minus 1 in that case. And that would have the effect of essentially, like if this was 0 and this was non-zero, it would basically swap the elements. And also, if B was negative, it would negate it so this is positive. All right. So whatever combination you have for A and B, it'll have this effect.
Okay, so I had two questions. The sine thing answered one of them, but my other question was, does it really matter if A21 is 0 or not? Because we know that diagonals are not going to be 0. Because we set that requirement last class that the diagonals can be 0, I believe.
Okay.
But A21 could be 0. But you said that would mess things up.
Oh,
Mess things up.
Oh, over here, you're working out this out. If A11 was 0.
Well, A11 couldn't be 0, could it? Because I thought before we said that it had to be positive definite.
Oh,
I guess it couldn't be if now.
Yeah, here A can be whatever matrix it wants, and also what's going to happen is, oh, okay, going back to this 2 by 2 case, that matrix A was not obligated to be positive definite. it only had to have full column rank. Yeah.
Okay.
A transpose A has to be positive definite, but as long as A had full column rank, it still would be. Yeah, okay. Yeah. All right. Now, geometrically, what this US rotation does is it rotates vector AB clockwise we angle theta such that C is equal to cosine theta, S is equal to sine theta. So to draw a picture, let's suppose this is your point AB. It's going to rotate it through the angle theta back down to the positive x-axis. So this would be your point R and 0. Yeah. Okay. All right. So, so this matrix by itself, if you had A was 2 by 2, multiplying by this G transpose, G would be your Q. That would be the Q of factorization. So now, how do we use this tool to reduce a general matrix to upper triangular form? Okay. Right, there's this really strange smudge on my notes here. It's like, I didn't do that, but, oh, a bonus piece of chalk just appeared. I might need that. Okay. Okay. Now, actually, okay, before I talk about how to use this for QR, I need to talk about these formulas for C and S. The formulas that we have, A over square root of A squared plus B squared, S equal to B over square root of A squared plus B squared. They're not both practical, and in most cases they'll be fine. But what if A or B is a particularly large number? And this is a homework problem that you would have both seen in 560. Because if A or B is very large, the square root of A squared plus B squared would overflow. And I assigned a homework problem from section 2.2, which allows us to rewrite this expression. And this is everybody has a hard time with this problem. Yeah.
I remember that problem very well.
Yeah, and I give all these hints and hardly anybody can get it. It's like, so.
I think I did some conjugate method in this.
Yeah, so we're going to compute this differently, and so we have two cases to consider. Here's what we do. So the first case is if B is the larger in absolute value. So then we compute P is A over B, so we're sure that we're not, if A and B are both 0, then we just don't do anything. Well, then G is identity. Okay. So I'll do a side case over here. If A equals B equals 0, then C is 1, S is 0, we stop. That's the same as B is equal to what I had. Okay, otherwise, one of these is going to be larger than the other. One of these is non-zero. So if B is a larger, So we compute this so that there's no concern about dividing by 0. And then we go ahead and set S equal to the sine of B. So this is 1 if it's positive, minus 1 if it's negative, over square root of 1 plus t squared. So here, t is less than or equal to 1 in magnitude. So we have no concern about overflowing. And then t is equal to S times t. Now, this is equivalent to these formulas here. If you worked it all out, gives the value. Now, there's a mistake in the book. I forgot the sign part. So that got fixed in the Python edition, but whoops. Okay. The other case is very similar. So A is a larger, we just flip things around. The roles of the A and B reversed, they're going to be over A. C is equal to the sine of A, or square root of 1 plus t squared. And S is equal to CT in that case. Yeah, that mistake carried over to here. So this is a practical implementation of getting the Givens rotation elements. Okay, questions about those revised formulas? Okay. So now suppose we have a general n by n matrix. We want to reduce it to upper triangular form with orthogonal transformations. How do we do it? It's somewhat Gaussian elimination like. So let's suppose we have matrix A, and I'm going to use X's to refer to non-zero entries or entries that could be non-zero. What do you do in this case? Now, I have a lengthy example in the notes. Although I should point out that that example in the notes is based on the erroneous formulas that forgot the sign factor. So if you were to implement Givens properly with what's on the board here and carry it out, certain entries would have the opposite sign. But the general flow of the algorithm is there. So what you do is, okay. Right. So okay, I need to find a function here. Take my notation. Okay. I'll get to find two functions. If I make a function that's called Givens, where the two parameters are A and B. So, so then you have C minus S, SC transpose, A, B is equal to R0, or R, I wrote this down before. So think of Givens as a function that gives you that cosine sine pair. Right. All right, so we'll call these helper functions. Okay. And then That's the first one. Then once you have a cosine sine pair, you think of G, capital G, IJCS, as giving a matrix that will take your cosine, the elements of this single gibbous rotation, and place them in the I and J rows and columns of an M by M matrix, where all the other entries of a matrix are 0, except on the diagonal where they're identity, or equal to 1. So it's kind of like when you have a unit lower triangular matrix that had just one multiplier sitting there. It's kind of like that, where you have identity except in the I and J row and columns, these 4 locations, you place the elements of this. Right. So using that notation, I can describe how you do Gibbons QR. On this example. All right, so if A is 5 by 3, that I've written over there. So you overwrite A with the first rotation I need to. The first we call our Gibbons function. And the idea is we're going to go from left to right, first column to last, just like in Gauss elimination. However, within each column, unlike Gauss elimination, we're going to start from the bottom and work our way up. The reason for that is a single Gibbons rotation zeroes out the bottom entry. So look at the 5 by 3 example. We want to eliminate the 5-1 entry first. So the second argument is the entry you want to get rid of. First argument is the entry that you're going to use to get rid of it. And so in Gibbons QR, it's going to be the entry right above. And then you overwrite A by rotating rows 4 and 5 with this cosine sine pair. And don't forget to multiply by the transpose, because that carries out the elimination properly. So now A looks at this structure. Which is stand right, so X, 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 X. I could be doing a lot of this. Now that one entry in the lower left corner is 0. What it does is, so it only affects these 2 rows. Because so actually I can show you what this matrix looks like in this example. Since okay. It's going to be a 5 by 5 matrix because A has 5 rows. The upper left 3 by 3 block will just be identity because we're only working on the last 2 rows. And then the rotation goes down here. So it'll leave these rows alone. It will rotate these 2 so that that entry is 0. Now, the rotation is determined entirely by these 2 entries, and then these get affected. Just like with a multiplier, you have the entry you want to eliminate and the diagonal entry you use to eliminate it to make your multiplier. And then that entire row I gets messed with. Yeah. So this here, acting on the first column, is doing this. And then you happen to carry out the same rotation on the rest of those rows, and it changes them in whatever way. Okay.
So we're essentially just working up the diagonal, just backwards.
Yeah, or up the column. Yeah, so we're heading, okay, well, I'll do
I'm
it.
talking about the G,
Oh,
like your G just kind of,
yeah, it's gonna move up.
Okay.
Yes. Okay,
So first, G transpose multiplies with A, then we get to 0, and then we move on with the
yeah, so now I'll show you the next part of that. So now it's the entry row 4 we want to get rid of. It'll be A3-1, eliminating A4-1. And then we overwrite A with, we have 3, 4, DS transpose A. So, and because the rotation will only affect rows 3 and 4, row 5, where we previously zeroed something out, will keep that, not that 0 entry. So then what would I do?
do the C as givens, but A2-1.
Yes,
A3.
A2-1, A3-1. And then we use given rows 2 and 3. Only rows 2 and 3 are affected. Right, and then we have to eliminate one more entry in this column before we go over to the next column and start at the bottom. Next column, start at the bottom again. And work our way up. Each time we go to a new column, we're eliminating one entry less. Now, practical implementation point though. We will not form this matrix explicitly because it's mostly identity. In a practical implementation, what?
Just deal with vectors.
Well, actually, you can form this, like this part right here, and multiply the appropriate rows of A by back transpose. That'll be fine. Yeah, so you can use like MATLAB's indexing to work on the appropriate row. What? Yeah.
This, okay, so you'd end up needing two nested loops. Because
Yeah.
doing this will go through a column, then you need to take
Yeah.
it through the column.
Yeah, so, okay. Okay, now I'll go ahead and show you like the pseudocode algorithm. Yeah.
All the Gs that we're looking for.
Yeah.
The product, right?
I guess take care of that too. Yeah, to get Q. Yeah.
Exactly.
So go through all the columns. A contrast from gas elimination. Gas elimination, we didn't have to touch the last column. But in that case, we assumed the matrix was square. A might have many more rows than columns, so we might have just having to eliminate every column. If we will, if A is not square. Actually gonna some initialization. So we're gonna build up the matrix Q and R. So the idea is we're in this case, this algorithm is not going to be destructive towards A. We're going to so Q will initially be identity, and we'll build Q up as we go. And we'll do all our elimination in R. I mean, if you pass your matrix A to a function and have it overwritten, at least it will still be preserved outside the function. But all right. At least the way this algorithm is written, it'll show you, okay, here comes A, and then we just get Q in our front. All right. So inside this loop, we're going to work on one column. But for each column, we have to work on the appropriate rows. So we start at the bottom. So that's row M. And we count backwards. All the way down to make sure I have this right. Yeah, J plus 1. So those are the row indices of the elements we're going to eliminate. Every one below the diagonal. So now in this loop, we're going to work on eliminating one entry. The entry Rij. So we get our cosine sine pair for a given rotation. A I minus 1j, then Aij. That is our target for elimination. Oh, sorry, not A, R. Because we set R equal to A, and we're doing all our work in R. All right. Okay. I should have given myself more room. What? Oh, cool. Right. Now I'm going to write this in a little more practical way than was done in the book. That's more MATLAB syntax. So if I form a matrix G to be C minus S, SC. All right, so we're going to do all our work of this. Oh, sorry. I can't call it G. Oh wait, yeah, I can. Okay. All right. So first I'm going to work on R, get R closer to upper triangular. So R will be overwritten by, well, but only rows I minus 1 and I. I'll use MATLAB's colon operator. And we're doing our work in column J. So we only need to look at column J through N. And we'll just rotate those two rows. So So that way it's only working on the portion of a matrix that it actually needs to. So that has the effect of eliminating the IJ entry.
Oh, okay, so you're just calling it G even though it's just the 2x2 that we're dealing with this actual.
Yes.
Interpretation for that iteration, and that's okay because we're free writing it every
Yes.
single time.
Yes,
And we don't actually need a final G. Okay.
right. We do need a final Q. Yeah, and I threw myself off, I was like, oh wait, yeah. Okay,
So when she multiplies, okay, previously we were all writing A.
yeah.
That's what's gonna be saved, R is going to be saved.
Yes. Yeah, so we keep whittling away at R until it becomes upper triangular.
We need to update Q at this point.
We do,
Okay,
and I'm about to show you how.
okay.
Okay, so with Q, we're gonna apply this give its rotation on the right instead of the left. So when you multiply give rotation on the left, you're rotating rows. Here we're rotating columns. So and the entire column. Okay, so it'd be so that'll be equal to, so those columns will be equal to themselves times G with no transpose. Now, to help you see that, that's why that it should go that way. If I apply a bunch of actually, I'll do it this way. Because I'm working my way from the bottom up. And that gives me to upper triangular form. That's supposed to be Q transpose. The Q transpose A is equal to R. So that means that Q transpose of a product is a product of transposes in reverse order. So this is the one that comes first. It was applied to A first. Each new one comes on its right. Because those the order is the opposite.
You're starting from the bottom, so the first one we find is actually.
Yeah.
Okay.
Yeah. Okay.
G is only when we place that 2x2 block in the identity.
Yeah, that's all this is.
That's all.
Yeah, yeah.
We take that block and we put it at
Yeah.
a given position.
Yeah, yes.
That's all.
Yep. And that's it. That's the whole algorithm. Okay. As far as the computational cost of doing it, so how many rotations we perform is going to be so in the first column, we got to eliminate n-1 entries. -1 plus n-2 and so forth, all the way down to m-n rotations. So that would be equal to mn minus Okay. Yeah. But then it's a matter of how much work does each of these rotations do? I think, well. Well, it depends on what column we're in. Like, all of the rotations working on the first column will impact entire rows. So, so what happens is you can scale rows. Well, it's gonna be a multiple of n. Certainly, because, okay, so what happens is you scale a row, okay. I think it's gonna be like 6n or so. I have to look more closely at that, but, because for instance, you take C times a row plus S times the other row and add them. So 3 flops per entry, and then again for the other row, different linear combination. So, okay, that sounds about right.
But you would still have to consider the operations to get C and S. Because to get C and S, that would take like 6. So to get those.
Order 1 per rotation, so I'm not gonna think about it. Yeah. Okay, so each, oh, I'm not gonna, we're not adding those. So really for what you should do is multiply this by this, this by this, this by this, add them all up, and then take this and multiply it by the number of flops to do a single CNS computation. The magnitude will be order mn squared. I was having to figure it all out. You can also see that if you just take this and multiply it by n. That gives you a magnitude, right? Well, it's pretty expensive. I mean, so imagine if m was roughly equal to n, we're talking order n cubed, like Gaussian elimination. So it's one of those expensive processes. Okay. However, it's a but here. If your computer architecture allows it, there's an opportunity for parallelism. For example, what you can do, like you could take rows 5 and 6 and rotate them, rows 3 and 4 and rotate them, something like that, independent pairs of rows, and make more progress that way. Like if you have disjoint pairs of rows. Now this algorithm rotates consecutive rows. You don't have to do that. So for example, suppose you use parallelism to get rid of all the, let's say, the even numbered entries below a diagonal. Then you can, then the odd ones are left, and you can use them to kill each other, and yeah, it's sort of a last element standing thing. So. Another use of given rotation is good for updating an existing QR factorization. Like, for example, suppose you have a matrix A and you take its QR factorization, but then you change the matrix in some way, like suppose you add a row or add a column, something like that. You don't have to compute the QR factorization all over again. You can use a few given rotations to update that QR factorization to account for a change. And because we're going to see other operations, other algorithms approaches to QR factorization in the next two classes. And those are not as good for updating, because given rotations, each one has very little effect. It's like it's like a very targeted operation. So it's more flexible. And each approach to QR factorization has its advantages and disadvantages. But I have to say on balance, probably givens is preferable, just because you could, because of the flexibility that it offers. Because here it's only each one is zeroing only one entry at a time. Next time we're going to see household reflections. In one of those wipes out a whole column. It's very destructive. And that's why I take the time to present multiple approaches to QR, because which approach is best depends on the situation. Okay. Also, what if the matrix is sparse? Givens is preferable there too, because if there's only certain entries below the diagonal you need to eliminate, you can just pinpoint givens rotations at each one. Whereas something like householder would do excessive work.
Going to run all of those elements anyway, regardless.
Yeah.
If for now we need to change them.
Yeah. Okay. And we're going to see givens rotations for a lot of things, like for solving certain eigenvalue problems or C-value decomposition, where we need to just zero something, but by performing the final transformation, this is how we do it. Okay. So, yeah, that's all I got.
It's a lot less pages than normal.
Yeah, well, I had several pages of notes, but one was like the examples. I'm not going to write all these numbers on the board. But you can just look it up there, and the numbers are incorrect anyway. At least they're correct in absolute value. Okay. Yeah. I've seen in Canvas that I have some items to grade, effectively not very many. I meant to do some over the weekend and forgot. How is homework coming? Any issues there? Or? Okay. We haven't done it yet. Or... oh, but that's
You know when
true. Yeah. All right, I guess we can call it good then. So householder next time. Oh, well, yeah, certainly since we're ending early.